So our last section of chapter 1 is about exponential functions and logarithmic functions. So when I'm given a function with any base b greater than 0, as long as b doesn't equal 1, because 1 to any power is just 1, so that'd be really boring. Then its domain is going to go from negative infinity to positive infinity, and its range, its possible y values, is going to go from 0 to infinity. So let's take a look at this. So let's say b is greater than 0, so as y goes to infinity, x approaches infinity. That's important to know. So if I have 2 to the negative 2, that means I have 1 over 2 squared, using our exponent rules, right, which gives me 1/4. If I have 2 to the negative 1, that gives me 1 over 2, which is just a half. 2 to the 0 is 1, 2 first is 2, 2 to the squared is 4, and 2 to the 4th is 16. So, as y gets bigger, so does our x. As our x value gets bigger, so does our y. It's important to note that even when I have negative exponents, in this case, my y value can never be negative. It's just going to get closer and closer to 0. It's going to approach 0. So here's the exponential graph of what we just did, right? We've got negative 2 is 1/4, negative 1 is 1/2, 1, 2, 3, 4, and so on and so forth. So our graph approaches 0 but never crosses 0, and that's why our range is from 0 to infinity, and our domain goes from negative infinity to positive infinity, so all real numbers. Things are a little different when we have a b value less than 1, so let's take a look at that. If I have 1/2 to the negative 2, that's really saying I have 1 divided by 1/2 squared. So 1 divided by 1/4 is 4. If I have 1 divided by 1/2, I get 2. 1/2 to the 0 is still 1. 1/2 to the first power is 1. And 1/2 to the second power is 1/4. So in this case, as x approaches negative infinity, my y approaches positive infinity, right? When my values are smaller, my y value gets, when my x values are smaller, my y value gets bigger. So its graph would look more like this. Still approaching 0 and never crossing 0. But for the smaller x values, it gets bigger and bigger and bigger. Some key points to take away are that negative 1, 1 over a are always on the graph. 0, 1, and 1 over a are on the graph. Well, why is that? So let's say we had f of x equals 3 to the x. If I have f of negative 1, that gives me 3 to the negative 1, which is 1/3. So I'd always have negative 1, 1 over 3 in this case. If my f in this for the same function was 0, any number to the 0 is always 1. So I'm always going to have the point x is 0, y is 1. And any function raised, any integer raised to the first power is just itself. So 1a is always on the graph. Okay? If a is greater than 1, then I have an increasing function. If a is a fraction, then it's a decreasing function, right? It goes looks like this on my graph. If it's less than 1, it looks like this, as we saw in our example with 1/2. The x-axis is our horizontal asymptote, right? Our value can never be negative. The domain is negative infinity to infinity, and the range is 0 to positive infinity. So it's nice to remember our exponent rules. So just a little refresher. If I'm multiplying two exponents with the same base, I add their degrees. If I'm taking an exponent to another exponent, I multiply it. If I'm dividing an exponent by another exponent, I can pull that out as long as they have the same degree. When I'm taking an exponent divided by another exponent, I can subtract the degrees. Exponents do distribute. And if I have a negative exponent, that's going to be a fraction. So if I have 2x to the negative third, it's important to know that that negative 3 is only on the x. So we would want to take 2 over x to the 3, right? We take our negative exponents and we push them to the bottom. Let's simplify a few more. So the first thing I want to do is distribute that exponent in. So that gives me 2 squared x to the 3 halves times 2, because I multiply them together, over 4 squared x to the negative 1 third times 2. So let's simplify that. I've got 4 x to the 3 over 16 x to the negative 2 thirds. I want to go ahead and simplify this. Let me look at my constants. That's going to give me 1 over 4. Then when I have an exponent divided by another exponent, I can subtract them. So I'm just going to have x cubed minus a negative 2 thirds. That gives me x 3 and 2 thirds over 4, but we want to write that as x to the 11 thirds over 4, right? I don't like mixed numbers. All right, now let's simplify this. I have 6x to the negative 3, y squared, so I've got 2 different variables I'm working with. So 6 divided by 12, that's going to give me 2 on the bottom, 1 on the top. X to the negative 3 minus a negative 4. And then I have y to the 2 minus 5. That gives me x to the negative 3 minus a negative 4 is just the 1. Y to the 2 minus 5 is y to the negative 3. So I'm going to put that in the bottom. So I have x over 2y cubed. So let's talk about e. E is a button on your calculator. You've probably seen it and you don't really know what to do with it. So e is a real number and not a variable in this case, right? E is found by 1 plus 1 over n as n approaches infinity. Okay, and it's notated like this. This is an example of an irrational number. It keeps going on and on forever, much like pi. So I wanted to make sure you took a look at that. We call e to the x the natural exponent function because e is greater than 1, it's increasing on its domain, and its range, it goes from 0 to infinity. The inverse of exponential functions are logarithm functions. Okay, so for example, the exponential function f of x equals bx is 1 to 1, its domain is negative infinity, positive infinity, its range is 0 to infinity. The inverse will be f of x equals log base b of x, and it satisfies this equation, log base b of x equals y, if and only if b to the y equals x. Okay? The domain of logarithms goes from 0 to infinity, and its range is from negative infinity to positive infinity. Remember, inverse functions switch their range. An example of this would be if I have 2 to the third equals 8, then log base 2 of 8 equals 3. So basically what logarithm is saying is if I take a log base 3 of 27, it's saying what power do I raise 3 to get 27? Well, that would be 3. If I have log base 2 of 16, it's saying, okay, what power do I raise 2 to get 16? Well, that's 4. If I have log base 4 of 16, that's saying what power do I raise 4 to get 16? Well, that's 2. And you could write that as 4 squared equals 16. You could write this as 2 to the 4th equals 16. So logarithms undo exponential functions. They're inverses. ln is the notation for the natural logarithm. That just means log base e of x. Okay? This is the inverse of the e to the x function. It's going to be natural log of x. So let's do some examples of logarithms. So if I have log base 3 of 9, that's saying, okay, what power do I raise 3 to get 9? Well, that's going to be 2, as we wrote here. Log base 3 of 27 is 3. That means 3 cubed is 27. What's log base 10 of 1 over 100? So what power do I raise 10 to get 1 over 100? 100 is 10 squared, so that'd be negative 2. Log base b of 1 is, what is it? what do I raise b to, any number, to get 1? Well, that's going to be to the 0th power. What if I have log base 4 of x equals 3? Well, that's saying 4 cubed equals x. So I could solve for x in this case. That would be 4 cubed, which is 64. So for log base a of x, these points are going to be on the graph. Okay, that's because if I have my log base 3 of x is -1, right? That's going to mean my x equals 1/3, because 3 to the -1 power gives me 1/3. If I have log base 3 of 1, what power do I raise 3 to get 1? Well, that's going to be 0. And if I have log base 3 of 3, what do I raise 3 to get itself? It's going to be 1. It's important to note that if a is greater than 0, then this is an increasing function. If it's a fraction, then it's a decreasing function. In this case, our y-axis is our horizontal asymptote, and the domain and range have switched from our exponential functions. So here we see a comparison, right? Here's my f of x equals 2x. Here's f of x equals log 2x. Here I have the asymptote for the function in blue, which is x equals 0, and my asymptote for the other one is y equals 0, the y-axis. And they're reflected across, remember this line is y equals x, and that's something that's true for all inverses, or the other one reflected across the y equals x axis. So here are some properties of logarithms, right? If I have two logarithms multiplied together, I can pull them apart. These are kind of undoing the exponential properties. You can play with those on your own or take a look at the book. It has a good example. Quotient property, when we're dividing, we subtract. I can distribute this to the front. Log base a of 1 for anything is 0, and anything raised log base a of itself is always going to be 1. So these properties hold, and these make sense. Note the natural log of e is 1 because natural log is log base e. These are equivalent, and e to the first power is e. So let's solve some exponential functions using natural logs. So if I take the natural log of 7x and the natural log of 12, I take the natural log of both sides. That means I can move this x to the front using the log of logarithms, properties of logarithms. So I have x natural log of 7 equals the natural log of 12. In order to solve for x, I can divide both sides by natural log of 7. So I have x equals the natural log of 12 over the natural log of 7. Now, if I have e to the x plus 6 e to the negative x equals 5, I want to multiply both sides by e to the x in order to get this e to the x to cancel out. So I'm going to multiply both sides by e to the x. That gives me e to the x, e to the 2x, plus 6 e to the x, e to the negative x, equals 5 e to the x. These e to the x's are going to cancel out. So I have e to the 2x plus 6 equals 5 e to the x. Now I want to get one side of the equation equal to 0. So I'm going to subtract e to the x from both sides. So I have e to the 2x, and it's 5e to the x plus 6 equals 0. Now this is in quadratic form. So I'm going to let u equal e to the x. And we're going to solve this by, is it substitution? We're going to solve this by substituting u for e to the x. So I have u squared minus 5u plus 6 equals 0. Now I can factor. Some factors of 6 that add up to negative 5 are negative 2 and negative 3. So I have u minus 2, u minus 3 equals 0. I can put e to the x back in. So I have e to the x minus 2, e to the x minus 3 equals 0. And I set these equal to 0. So I have e to the x equals 2, e to the x equals 3, because I set each of these equal to 0. Now in order to solve for x, I'm going to take the natural log of both. Remember that the natural log cancels out. The natural log of e is just 1. I can move this x to the front, so I have x natural log of e equals 2, which is x equals 2. And the same thing will happen over here. So I will get x equals, the natural log. I had to take the natural log of both sides. I get so excited when we're solving equations. So x equals the natural log of 3. Because remember, what I do to one side, I need to do to the other. So those are our two x values. Now what if I have e to the x squared? I'm going to take the natural log of both sides. That gives me the natural log of e, and I can move this x squared to the front. So x squared equals the natural log of e, which equals the natural log of 200. The natural log of e cancels out, so I have x squared equals the natural log of 200. I'm going to go ahead and take the square root of both sides. So I have x equals the square root of the natural log of 200. Next, I have the natural log of 1 over x equals 4. I'm going to rewrite this as, I'm going to take, let me look at my notes real quick. So I have that the log base e of 1x equals 4. So I can rewrite this as e to the 4th equals 1 over x. Now I can solve for x by multiplying both sides by x. That gives me x e to the 4th equals 1. And I can divide both sides by e to the 4th. So I get x equals e to the 4th. See, there's lots of tricky things we can do in order to get x all by itself. Next, I have the natural log base 10 of the square root of x plus the natural log base 10 of x is 2. Okay, I can combine these two. Remember that the square root of x is x to the 1/2 power. So I have the natural log of 10, x to the 1/2 plus x equals 2. So that means the natural log of base 10 of x to the 3/2 equals 2. Now I can move this power to the front. This is really log base 10 of x to the 3/2. So I'm going to move this to the front. So I have 3/2 log base 10 of x equals 2. I'm going to divide both sides by 3/2. I get log base 10 of x equals 2. Divided by 3/2, that's 2 times 2/3. So that gives me 4 over 3. So now this is saying 10 to the 4/3 is what? We can rewrite this as an exponent. Okay? 10 to the 4/3 is x. And that's our final answer. So let's go through a couple more examples because I want to make sure you've seen all the possible types of problems out there involving logarithms and natural logs before we're almost done with chapter 1. So if I have the natural log of 2x minus 3 the natural log of x squared equals 0, we're kind of going to work backwards with the logarithm properties here. I want to bring this 3 over here. Remember, before I could move this over here and multiply by 6, but I want to get this condensed into one logarithm because one logarithm is so much easier to work with than 2. So if I have the natural log of 2x minus, I'm going to move this 3 back over here, so I need to multiply them together, the natural log of x to the 6 equals 0. Now I can combine these two. When I'm subtracting, our logarithm rule is that I'm dividing. So now I have the natural log of 2 over x to the 6th equals 0. Now it's important to remember that natural log is log base e. It's also important to remember that if I have 2 to the x over x to the 6th, I can cancel out one of those x's, so now I have 2 over x to the 5th equals 0. So e to the 0 equals 2 over x to the 5th. I'm converting it from a logarithm to an exponential. Well, e to the 0, any number to the 0 is just 1. So I have 1 equals 2 over x to the 5th. If I multiply both sides by x to the 5th, I get x to the 5th equals 2. If I take the 5th root of both sides to get rid of the exponent, I have x equals the 5th root of 2. Again, a very similar problem. I have the natural log of x cubed minus 4. The natural log of x equals 1. So let's practice again, working backwards to condense this into one logarithm and then writing that as an exponent. So if I have the natural log of x cubed minus, I'm going to move this 4 over here, the natural log of x to the 4th equals 1. When I'm subtracting, I'm really dividing. So I have the natural log of x cubed divided by x to the 4th equals 1. That's going to leave me with the natural log, so log base e, of 1 over x equals 1. So this is saying e to the first power is 1 over x. So I'm going to go ahead and I'm going to multiply both sides by x. That gives me xe equals 1. I divide both sides by e. I get x equals 1 over e as my final answer. So, rule of thumb is when you're given a problem with an x as an exponent, you're going to use natural log to solve. Okay? So if you're given an exponent, you go to a logarithm. And if you're given a logarithm or a natural log, you're going to convert to an exponent. Okay? Remember, they're inverses. One undoes the other. So it makes it a lot easier to solve these types of problems. The last thing I want to talk about is change of base formulas. So if I have a an exponential and b an exponential, I can write log base a of x equals log base b of x over log base b of a for any real number. And we can use this to change our base. So this means if I have log base 3 of 7, okay, let's let b equal e, okay, that means I'd have log base a of x equals the natural log of x over the natural log of a. So for log base 3 of x, we're going to write this as the natural log of x, which in this case is 7, over the natural log of 3. How about log base x of 6? Okay, I can rewrite this as the natural log of 6 over the natural log of x. You want to change the base to something easy to work with. I could also, if like b equals 10, this would be log base 10 of 6 over log base 10 of x. But natural log is something we know and it's easiest to work with. So you want to use the natural log all the time.